Good afternoon, everyone. Welcome to the session. Xamishka up. And I was thinking, because she showed such high-level chairman skills last time, we have to go to our professional chairperson here, Pelani. So, Pelani, will you take over for us today, please?
Hopefully, I can match up to last week's quality, but we'll see how that goes. Yes, good day, everyone. Good to have you all here. Again, we are back for our prestigious weekly seminar series. Today, we have a very interesting presentation by Xamishka Jaglal. Many of you guys are very familiar in our group, the concept of industrial symbiosis. It's a big part. It's something novel. It's something different, and it's a big part of the research that we're currently conducting. And today, Xamishka will be presenting on the application of machining algorithms for AI for automation of functional substitution in industrial symbiosis. So I would like to hand over to you, Xamishka.
Thanks, Phil.
Minus 10 for the chairman skills there.
Okay. All right. So thank you, Phil, for that very warm introduction. Just to recap on my heading. So I am working on the application of matching algorithms in artificial intelligence for the automation of functional substitution in industrial symbiosis. So let's get straight into it. So I joined the group at the beginning of this year, and I started my work with Prof on an aspect, or rather the company matching aspect of the Chemicals Without Borders project. And this has led me to building up quite a few many skills throughout this project. The most important ones, I'd say, were the ability to extract text from documents and websites. And I'll get into this in a bit more detail later on in the presentation. Another important skill that I'd come across was the use of natural language processing, as here I was able to process the text that I had extracted, build programs, and classify this text into clusters and homogeneous groups. Again, we'll speak a bit more about this later on in the presentation. So this ties into the CWB project when we look at the actual company grouping and the pairing of symbiosis partners. So that's the general gist of my project and what I've been working on. So let's get straight into it, like I said. So to first understand why the project is necessary, or why my aspect is necessary, we must first understand the problem that's at hand. Now, like Pelani, you mentioned, a couple of us are working on the CWB project, so I'm not going to go into too much detail about industrial symbiosis, but the general idea about it is that it really is a step forward in paving the way for a circular economy, in that it reduces waste and the strain on natural resources. Now, there is an industrial symbiosis project in action in Kalundborg, which is a small city in Denmark. Now, when I looked into this project, it wasn't planned carefully. It was just 4 companies in close proximity to each other, where the foremans just started speaking to each other and decided, okay, we have grounds for maybe initializing some industrial symbiosis between these companies. And it took them about 50 years to get the project off the ground. And that was purely because they were just doing it via word of mouth and just speaking to each other and saying, okay, these are the processes that I'm working through. This is what I have available. This is what I need. So this inefficiency has caused that simple industrial symbiosis project with only 4 companies to take such a long time. So now imagine if you wanted to scale it up to 90 companies, which, by the way, is the number of industries in the Prospectin Industrial Park in Durban. That's how many companies there are in that vicinity. So imagine now you have 90 foremen there trying to figure out what the other 89 companies need, and you're trying to find good pairings and matches between these few manually. That's not going to work out very well. If it took 50 years for 4 companies in Denmark, imagine how long it's going to take here for 90 companies in South Africa. That would take a really long time to get off the ground. So the point that I'm making here is that the scaling up of the project and sort of including more companies leads into a really big mathematical problem. And this problem can be solved, or rather, effective industrial symbiosis can be reached when we automate the grouping and matching process. And that's where my work comes in. So today I will be taking you through a couple of the steps and processes that I've been working through. And I'm going to try and keep it as simple and as short as possible. So the first step in my process was to develop my databases. Now, I've worked with a total of 3 databases so far. And the first one I built was one that composed of journal articles hailing from 4 major topics. That's coronary heart disease, COVID-19, industrial ecology, and heat exchanger design. Now, this corpus, or this test corpus, as I like to call it, was actually very important for my study, because this is how I sort of tested the matching algorithms that I developed, and I was able to calculate the accuracy and the performance of the algorithms. Because for this corpus, I actually knew what the output was supposed to be. I knew which documents should be grouped together and which ones should be kept separate. So in knowing this and sort of having the supervised column on one side, when I got the unsupervised column from my algorithms, I was able to compare them and get an actual numeric accuracy to see how it worked. And this now allowed me to discern whether or not the algorithm was good enough to progress to a corpus where we don't know the final result, and to see if it would be able to perform well in that case. So this led us to working on the next corpus or database, which was the company annual reports. Now, this was a bit of a problematic database because annual reports tend to focus more on the shareholders and the financial viability of a company. So they talk more about their sustainability issues, the cash flow throughout the year, not really focusing on the crux of the company, which is the process and the chemical constituents, because that's what we need. So I tried to get around this by building a dictionary, or rather an exclusion list of all the financial terms that I could exclude from the database, just so I could sort of push the financial terms to one side and really extract the root of what the document's about. And it did help to an extent, but it didn't lead to the groundbreaking grouping that I was looking for. So keeping that in mind, I had to now think of a solution of where I could find information about companies that was readily available. Because I mean, at the start of a project, when I'm trying to get things off the ground, no company is really going to give me access to all their databases and all their information. So I had to find something that was readily available. And the thing that I came up with was the company websites, because on this platform, companies and industries, they boast their products. They boast simple process descriptions, their locations, value and mission statements, and basically everything that I needed to discern what the company was about for all the companies. So this actually turned out to be my most important corpus, and it's one that I'm currently developing as I go along. And we'll see a little bit more about that later on. So after I'd sort of built my databases up, the 3 databases, I now had to extract the text from these PDFs, which is from the journal articles and the annual general reports, as well as scrape the websites from my website corpus. So just a little bit about the PDF extraction. We see a little piece of my code here, where I simply search for every document that has the extension .pdf. Now, this allowed us to only look at the important documents, not involving any system files or maybe other documents that are contained in the same folder. So this really helped to streamline it to the exact documents that we were looking for. Now, the rest of this code involved sifting through every page in every document and appending them into a list, and then appending all the separate documents into a new list. So at the end of it, I had one list of strings where each string was a separate document. And it ended up being quite long, as the test corpus had 36 papers and the annual reports had about 43. So yeah, that was how I extracted from a PDF. Now, web scraping, for this, I simply picked the URLs of the companies that I wanted to extract or include in my database. So take Sasol, for example. I just copied the URLs from all their links, for example, the products page and everything else, and I appended those into a URL list. Now, then I used web scraping to actually get the information off those pages. And I don't want to go into too much detail there as well, but the general idea of web scraping is that you request access to the HTML script of a website. Now, almost every single time you do get access, because nobody really guards their HTML script. But it was just one company that I'd come across in about 40 plus companies that restricted access. So what I mean by that is, if you're looking to extract information from a company's website, chances are you're most likely going to get the information from there. Now, in developing this web scraping algorithm, when I was testing it and developing it, I actually tested it on a Facebook page. So I literally just took the URL for Facebook page and put it in there, and it worked. It did scrape all the words of the memes and stuff from the page. So groundbreaking stuff right there. So once I had that database of words now, so it went from having PDFs and links to now having the actual strings from all these documents and web pages. it now needed to be processed and cleaned before it went into my algorithms. So I'm just going to explain the pre-processing here with a simple example. So at the top, we see these two strings that contain capital letters, punctuation, white spaces, numbers, and words that are not in their root form. And by that, I mean presenting and presented, which both have suffixes. They're not in their root form, which is present. So by running my textual pre-processing algorithm on it, we see the two strings that come out there, where there's no capital letters, words have been brought down to their root form. And I also went with the option to remove numbers. There is an option to convert numbers to words. So in that case, 2020 would become 2020. Now, initially, I had chose to go with the convert number approach as opposed to completely removing numbers. But I found that it didn't really have a bearing on my results because I was just looking for the general idea of what companies were doing. I didn't care that they were processing 3 kilotons of coal. I just cared that they were processing coal. So I just chose to remove numbers altogether. Thereafter, I changed it from a string into a list of tokens, as you see here. And the final pre-processing step was to convert it to a numerical basis. And this was done using term frequency, inverse document frequency, or TF-IDF. And you see the results of that here in this table. So the first algorithm that I sort of investigated was the K-means algorithm. And the first step for K-means was to determine the number of clusters, or rather the number of topics available in each document. So I provided an initial guess and a range over which the number of clusters might be contained, the optimum number of clusters might be contained. And for every number, you calculate the inertia. Now you're looking for the minimum inertia. So this is a bit technical, but the idea is to find the first local minimum on the graph of inertia versus the cluster number to find the optimum number of topics. That's basically the crux of K-means and how you get that optimum number of topics that's contained in a database. So after that's been run, you can find out about what each cluster or topic contains. And we see it here on the right, where you can tell cluster 0 or first cluster is about COVID-19. The second one is about industrial ecology and so on. These are the latent, not latent topics, but these are the keywords that come out from each cluster. Now here we can see a nice visual representation of our clusters, where each colored point represents one of your documents, and the gray centroids come from the K-means algorithm. This is really to help us visualize what it is we've been doing and to make sure everything's been grouped correctly. So here we can actually see our 4 clusters and our 4 topics as they are. On the right, there's a piece of a table, and this is actually the table I used to calculate the accuracy of the K-means algorithm. Because if you remember, I mentioned this is my test database, so I already knew which document belonged in which cluster. So looking at this was the result, a piece of the result from the K-means algorithm. I merely compared this to my supervised clustering, and then I could get the accuracy of K-means, which was 100%, by the way, because I used 4 very different topics that could easily be told apart. Now, there is a problem with K-means, and that is it only looks at the most pertinent topic in a document. So say, for example, now you have Sasol, who might talk about mining and chemicals. K-means is going to look for the most prominent one, which might be coal mining. And it'll say that Sasol is only about mining and it can't be grouped with chemical companies. Now, this is not going to be really useful because if we really want to create good industrial symbiosis, we need to know what are the different topics in each company to create different pairings. Otherwise, you could just do it the manual way, I guess, because we really want to see what each topic is about. So that's where LDA comes in. Now, the first difference I noted between LDA and K-means is that K-means kept things as an individual, it kept documents or papers or companies as an individual entity, whereas LDA used a bag of words approach. So what that means is I literally generated a dictionary of every unique word from every document, no matter where or which document it came from. It just needed a list of every word that existed. Now, without going into too much detail about the equations in LDA, there are 3 main parameters that needed to be solved for, and that's the number of topics, alpha and beta. So here on the right, we see I vary the number of topics and I calculated the coherence because we want the best combination of number of topics, alpha and beta, to get the highest possible coherence while keeping the number of topics at a minimum. So we can see here, I picked 6 as the number of topics, and that resulted in a coherence of about 65%. And this is what I mean by the topics. Here we see, okay, let's take topic 5, for example. this is the general topic or the latent topics that come from topic 5, or actually the 6th topic. The word mine makes up for 2.4% of the topic. Similarly with mineral, it's 2.3%. And these are just the top 5 of the results. If you print them all, you'll find that if you add up an entire string, it'll add up to 100% or 1. Now, this is where the true value in LDA shows, because not only are we saying a document or a company is topic 1, yes, it is about topic 5. So yes, it is about mining and resources. We can tell the actual percentage of the document, how much is it about mining and how much is it about chemicals, for example. So let's look at BASF, for example. Here we can tell it's 16.5% topic 0 and 83.42% topic 3. So that becomes really useful when we're looking at industrial symbiosis pairing, because not only can BASF be paired with other mining companies because of topic 3, they can be paired maybe slightly or in certain aspects with companies that are also grouped in topic 0. So this really helps to open up more options and find more pairs for industrial symbiosis. Now, the algorithm that I'm currently working on is identification trees, or ID trees. And as I mentioned, I'd converted my databases to a numeric value. And we see an example of it here in table A. So initially, this was done on my journal articles or test corpus, by the way. And initially, it had 18,000 dimensions. That's 18,000 different words that were included. Now, I reduced that all the way down to 3 dimensions using singular value decomposition. But as you see, these are continuous variables and it's very, very specific. So before feeding them into the ID tree algorithm, they needed to be classified into simpler categories and then run that table into the ID tree algorithm, which we see here in table B. So if we look at dimension 1, entry 2 and 3, we see 0.33 and 0.25. These are fairly close together. So when I did my classification, which ranged from -1 to 1, by the way, and I broke it up into 10 classes, we find that both of those numbers belong to class 7 here. So that really, really simplified the database prior to going into the ID tree algorithm. This also yielded an accuracy of 97% when it was brought from 18,000 dimensions to 3 dimensions. So that was fairly good. And the ID tree, as it currently stands, also has a recall of 0.75, where the recall is the true positive rate. That means if something is positive, the algorithm analyzes it as positive. So the ID tree algorithm itself worked fairly well on the classified documents, that's table B, instead of the super specified documents that is in table A. So this is an example of what I'm trying to achieve in this project. So far, I've come up with these groups of companies, and I have quite a few others, but I've just only shown these 2 here. What we're aiming to do is really look for companies that can be grouped together based on what's in their information, what they've provided to us on their website. I guess with more detailed information about each company, I could find more pairings for them. But for now, what I've developed on my own, this is what I've come up with. And there are many others just like this. So this is what we're looking to do. And this is what I'm trying to expand on. So I know I did go into a lot of detail about the actual methods that I was working on. And that should be Biden, by the way, my bad. So let me just step back and talk about why it is that we're doing what we're doing. So we're really trying to push for a circular economy that drives sustainable development and that's mutually profitable. Because if you're going to try and sell it to companies to involve themselves in our industrial symbiosis project, yeah, you could tell them, okay, you're working towards a circular economy, helping the environment, they'll be happy to do it. But if you tell them that it could be mutually profitable between you and the person that or the company that we're going to pair you with, it then becomes a lot more attractive. And you can really involve a lot more companies in the project when marketing the mutual profitability that comes along with it. Other than that, the automation of the process, like I mentioned earlier, by automating this process, we can include so many more companies. And by including more companies, we can find more pairs and more sort of industrial symbiosis partners to create in areas. And that can really help push towards our goal, a sustainable development goal. Also, by automating it, as I mentioned, by the foremen speaking to each other, it's much more efficient and more accurate when doing it, when automating the entire process, instead of doing it manually by going and speaking to people and emailing each other process descriptions and stuff like that. So this sort of takes the human aspect out of it and sort of has everything done for us. So that's really what we're looking for here. So the next parts that I will be working on is extending my website corpus. And by that, I mean I'm going to find more companies to scrape their websites and sort of include more information and more companies into the website corpus so I can find more industrial symbiosis pairs just on the rudimentary information provided on their websites. So that's one of the big selling points, and that's what I'm moving forward with at this time. I'm also looking to calculate the accuracies of the other algorithms that I've developed and a couple others as well, just to sort of make sure they work well and to prove that this is how they work on a test case. So when using them on a database or corpus where we don't know the final result, we know it'll perform well. And lastly, I'm going to complete the ID tree algorithm where we can generate this really nice tree with the nodes and leaves. So we can actually see how it's classified from this giant database into smaller homogenized groups. Thank you for listening to my presentation today.
Xamishka, very wonderful, very informative presentation. I would like to open the floor for questions. So if you have a question, just raise up your hand, or you could use, I don't know, is there, I can't see a raise up your hand reaction because some of you guys I cannot see. But you can also just use a thumb up reaction if you want to ask a question. Yes, Sudain.
Thank you, Phil. Thanks, Xamishka, for the presentation. I just have a quick one to start. You spoke about, you have like a kind of a sample of your corpus which you worked on, and you want to now include more databases, and you want to broaden your database for analysis. So how well does the algorithms which you're using and also the ones which you intend to investigate, do they scale up quite well? Because if you're all linking this together as a group, or we're going to use your work in our work as well. So I think scalability is quite a significant thing to comment on.
Okay, so if you see here, my test corpus, I initially used 4 topics. So that was a fairly minimal, very small, database that I developed, and it performed well there. Then after that, it really got tested, or the scalability was really put to the test in the website corpus, because here we had many more companies, and also these companies didn't have one single topic. Like in the journal articles here, like I said, they come from 4 main topics. So when I tested it on the website corpus, and just from a general understanding of what each company does, also if you just read up on the internet and stuff like that, just to check, I found that I did get some really good groupings between companies when it really was scaled up. So by scaling it up even more, based on the results I got from the website corpus that I currently have, which is about 30 something companies, I foresee that it will work for more companies than that as well.
Okay, thank you, Sudain. Thank you, Xamishka. And Prof?
Thanks, Vlani. Thanks, Xamishka. On this, I'm glad to hear you are thinking about how to find these complementary matches, because the whole point of this is you want to match suppliers and consumers together. And you've mentioned a bit about looking at what other clusters you seem to be fitting into. And I'd like to just give you a chance to comment on that further, because in principle, every company has some involvement with every cluster, and we select the kind of home-based on the highest matching value. But if you are possibly connected with every other cluster, how then do you identify which ones are actually complementary? And I have a sort of thought on that, but maybe you can comment first there.
Okay, so how I saw it was, I did mention that the algorithm that works best for the website corpus, like you mentioned with companies, was LDA. So how I'm going to find the complementary matches here is by the percentage similarity to each topic. Like, let's look at air liquid, for example. It's 99.9% topic 3, and so is Anglo-American for that case. So by looking at the percentage similarities to topics and companies, we'll be able to find which ones should be grouped together. And then for those more refined topics that you were talking about, we can look at the smaller similarities. Like here, it's for BASF, it's 16% topic 0. So for our initial pairings, we can obviously go with the majority percentage, which company resembles like a larger percentage to which a topic. And then for more refined clustering and grouping from there, we can look at their smaller percentages. But the general case is that most often they do belong to one topic or cluster. But I guess in the cases of Sasol and other companies, they do belong to at least 2 or 3. And then we can look at them in terms of weight, like which one they're most similar to, and then go down from there to find the more matches, I guess.
So you see what I'm saying is, I think you'll get one entry that has a nice high value and clearly fits in that cluster, and you'll get low values for all the others. And it's going to be difficult to say, that low value cluster, seems to be a complementary one. They'll all have a similar low value. So I was thinking, what could be done is when you are doing your text processing, so before you are at the stage where you are actually creating your clusters, that you first filter the text, and you do two types of filters, one for the producers and one for the consumers. So if the chemical seems to be consumed in one case, then you eliminate those sentences that are talking about consumption or words like consumption. And in fact, you might need a third group so that you can classify between consumption. You can create a cluster where you cluster sentences, so like a pre-processing clustering step where you cluster sentences that seem to be more about consumption and others that are more about production. And then you filter your document. So you separate your document into those parts about consumption and those parts about production. And then once you do that, you would be able to, you would then do, things like LDA and other algorithms twice. You would do it once for the consumers and once for the or for the consumption sentences and once for the production sentences, and then you would then you would have your two complementary groups, and then you'd be able to do the matching. So that's just one suggestion about how you could actually form those partitions and groupings.
So you mean sort of cluster and separate a document on its own entity first, and then from there run it through the entire thing with every other document? Yeah,
so you want to know which companies which ones are consumers of a chemical and which ones are producers of a chemical, and then you'll be able to make complementary matches. I think what you have currently is actually showing some complementary matching, and that's just because in some of the documents they do mention what they are consuming and what they are producing. So, but you might be able to increase the accuracy of your matches if you do a partitioning into the two types of partner.
Okay, well, thank you.
Right.
Thank you very much, Prof. Are there any other questions? Yes, Sudain.
Thank you, Phil. Xamishka, okay, so can you go back to the slide where you spoke about the corpus that you used, where I think there was heat exchanges and there were some other things there.
This one?
No, go more earlier than this. Yes, this one. So you have CHD is the heart disease one, the coronary heart disease, then COVID-19, industrial ecology and heat exchange design. So these topics are kind of, it's like one in the medical field and one in chemical engineering, and COVID is also medical and so on. So they kind of split up. So what happens if you have topics which are kind of from our use case? So if you have like pressure vessels and like a batch reactor and continuous pump and so on and so forth, where when you actually do the LDA on these concepts which are from the same field or from aspects of a chemical plant, for example, there'll be similar keywords. So there'll be like keywords which are closer together or more closely related, or repetitions of keywords. And then when you go about trying to classify them into either one kind of table or another, or one kind of database or another, does it work well in that situation where the topics are not easily distinguishable one from the other, where the tokens are more or less similar, or where they may be overlapping?
Okay, so like I mentioned, I did pick 4 way out there topics because I wanted it to be simple enough just to test the algorithm. But in the case like that, yes, I think it would, because if all of it is about the general chemical engineering processes, and I mean, if you're looking at the companies, that's what you're going to have, all the units that are there, the batch reactor and the stuff that you mentioned. So having all those there, it would be able to split it up. There would be a problem, however, if, like, say, for example, there's a couple papers talking about different units, like all of them grouped together in one document. And say you have like maybe mining papers that have complete like earth moving equipment and stuff like that. So it would then group it into 2 clusters. So in that case, the units that you were talking about would all be grouped together. But I know Prof and I actually talked about something called iterative clustering, where say you have these 2 very broad clusters now. One was about earth-moving mining equipment, and the other is about technical chemical engineering equipment. If you were to run the algorithms again on these separate clusters on their own, you'll be able to break those 2 broad clusters down even further into smaller, more specific groupings. So in that case, from that general chemical engineering cluster, it'll break down further into heat exchangers, batch reactors, and stuff like that. So it'll split it up into the topics even further after that in the second round. And in theory, what you can do is you can break it down so much further that you bring it down to one separate thing at the end. You should be able to do that, but I mean, there's really no point in doing that, but you can bring it down to extremely specific singular entities.
Yeah, that's good to know, because why I was asking is because, whoever works with the data after you classify them into databases, my concern was like if there was one term, like for example, a pressure sensor. So if you have like a pressure vessel or a batch reactor, there'd be pressure sensors in both of those situations. And then when I saw the graph of the centroids, so I was just thinking, my concern was if the centroids overlap, or if they're too close together, I wasn't really sure what that meant for as far as the classification is concerned or algorithm investigation. But now that you've explained, it's a bit easier to understand.
It wouldn't really matter, because if there's 2 centroids, that means it's 2 completely different topics. So yes, if they're close together, it means that they're about like a general in the same vicinity, like maybe CHD and COVID-19, for example. But if they have 2 separate centroids, then it means it's 2 different topics, and you'll be able to discern between the 2.
Okay, thank you.
Okay, thank you very much. Are there any other questions?
Maybe just on that point, if I may, if you've got 2 centroids so close together, you see the algorithm doesn't work on a fixed number of centroids. It's not like you say, I want 4 centroids. It works. It tells you how many centroids, and it recommends a certain number of centroids that best fits the data. So if you do actually have 2 centroids so close together, then it's actually going to create 1 centroid out of that. And then as you mentioned, if you want to iteratively further subdivide that, then you can do that. But if in the first instance all those documents are so close together, then you'll likely get 1 centroid in the first instance at least.
Yeah.
Okay. Before I ask, I mean, I have a few questions. But before I ask, is there anyone else who has a question? No. Okay. The first question I have, I think it's probably a dumb question. So I know you looking at web scraping and reports. So there are those fuller words like is, the, for, and so forth. I was just thinking, because it might take some time to to process that. So just a suggestion, you can, first, as I think Prof mentioned about filtering, you can also, filter those words. And also because, you're in the chemical engineering domain, there are some of these common words in the field of chemical engineering that you're going to expect, to be present in all the documents. Because, Sudain also spoke about scalability. That's what you want at the end of the day. You want something that can manage a big set of data. And when you look at scalability, it's about measuring, being able to process a large data set, but also process it at a good time, in a good processing time. It's no use being able to process 1,000 documents, but if it's going to take you maybe 6 months or so. So that's one thing you can consider to reduce computation time. And also with regard back to that point of scalability, I mean, I'm seeing that you are looking at different methods. You evaluating K-means, you evaluating the LDA, and I think you're also looking at decision trees.
Decision
trees.
Yeah.
So as well in your computation, a good variable to also track is the processing time involved, because that's it's going to be a significant indicator of how efficient and how scalable your algorithm, your methods are. And if you want to choose between these ones, which are the best, it's also a good benchmark for you to benchmark them across. That's just some points. Regarding your whole experimental setup, do you have a specific set of companies that you're targeting? Because I know you said there are about 94 companies. How are you defining your limits, your how many companies you're operating and so forth?
So when you mean like how I'm picking the companies to include?
Yes.
Oh, no, I'm not. I'm trying to make that as broad as possible, because the truth is, in an industrial park, like I talked about Prospective, let's just speak about that for a little bit. There's no generalized cluster of them that are doing the same thing. They're spaced out very broadly. So you might have a steel industry next to a chemical factory of some kind. So what I tried to do was include companies from all the industries. I did try to keep it to chemical and process engineering. What I mean by that is I didn't include financial institutions like banks and stuff like that. I tried to stick to the more chemical and process companies. So I picked anything ranging from mining companies to mineral companies to chemical, petrochemical, and stuff like that. So I just tried to stay in that one aspect, but in that aspect, picked any company from there. I didn't restrict it to a certain form or type.
Okay. All right. Just because it's something that I'm also, working on, defining that experiment effectively, okay, I'm working with these companies, how are you selecting them? As you said, okay, these companies, they're chemical companies, these are the characteristics and so forth. But this is just more for, your right type point of view. You want to have, this is my experiment. These are the companies. These are the methods that I'm testing. So it's just some advice I wanted to share with that. When you choose your companies as well, have that criteria. As you said, okay, I'm choosing companies that are A, B, C, and D. And, these are how I'm choosing it. Also, I know you're testing the methods as well. When you test them, have that, I don't know, I'm not sure what value are you using to benchmark their accuracy.
That's just based on how they perform against the supervised data that I provided. Because I know I spoke about the known database that I know the results to. So I just checked the results from the algorithm to see how it performed and compare it to the manual or supervised clusters and things that I gave it. Because I know what the answer should be. So I'm checking what the answer is from the algorithm and then comparing them.
Okay, and then, but for your real test case, I mean, so are you also, do you have also supervised solution for, that cluster that is in prospection?
No. That's more difficult to create a supervised one for. I guess you can, because I mean, if you read the documentation for each company, you can tell what each thing is about. And I guess you'd have to make a note of it, but I haven't implemented any supervised information or clustering on that corpus. It was just purely for my test case. And that's where I sort of tested the algorithms to see how they work. And then once it performed well enough in the test case, I just scaled it up to my website case. Because I sort of viewed it as that's the end, not end goal, but that's what we want to do, where we have all the company's information. And if I tell you, Phil, I have company A and B, tell me what each thing is about. Do you think they'd be a good pair just by reading them? So by testing it where you do know the examples, like here, you can see how it performed with coronary heart disease and COVID-19, because they both had a lot of medical terms, very similar medical terms, but it was still able to tell which ones were about coronary heart disease and which ones were about COVID-19. So by the fact that it was able to discern it, and I guess I understand what you're saying, maybe I can include something that's more similar, like for heat exchange and design, like Sudhir mentioned as well, maybe I can get some papers about pressure vessel design, just to implement a bit of complexity in the test case, and then see how it performs there. So it would perform analogously for the website case where I don't actually know what the clusters are or what the topics are.
Okay. All right. Okay. Yeah. Okay. No, maybe because I'm just thinking now. So maybe I'm just thinking maybe it was just a misunderstanding of. So basically, you are testing these methods on this test corpus that you know, and then from the test corpus, you're going to choose the best method there to test the prospection.
Yeah.
Oh, okay.
But I actually ran all of them on the website corpus, even though, like I mentioned, KMeans didn't work so well because it just went with the most prominent topic, which is not the case with companies. From the test corpus, I figured out that LDA would be better. So from the test corpus, I was able to figure out which one is the best, like you mentioned, and then use all of those on the website corpus.
Okay. All right. Yeah, just something to think about. You know, in your test corpus, just think about how you would, decide that, this one is actually better than this one. Because, as you said in the K-means, I think you said something that it was, what you said, what was the K-means doing?
The K-means was trying to group things based on one cluster.
Yeah. So, so just, just something to tell you from which you can say that, hey, based on this this benchmark, this method is actually performing better, than the other, and this is the method, that is best for this industrial symbiosis setting. But it's just more for like reporting, because these guys, they can get. Prof and I would know. We've been through a lot with how they can get very critical in how you present your results and your discussion. But yeah, it's good. Yeah, it's looking very nice.
See, in my head now it makes sense because I've been working through it. But now I didn't realize that for an external person now to say, how do you know this one's better than the other? Because I actually ran them and wrote it myself. It's easy for me to just know it, but I need to be able to state that properly for a reader to understand. So thank you for those points. That'll really help me with my write-up and discussion.